Okay, so let's say that point right there is a again. Okay, and the slope at that exact point, we call it f prime at a, or dy over dx, right? By Leibniz notation, dy over dx when x is equal to a. Okay. Okay, look. So if I pick a delta x, so let's say I want to move a little bit up. So this is delta x, which makes this a plus delta x. Okay. And this length here, just up to there, just up to the function, is the delta y. Okay, just up to the function. Now delta x, I'm gonna if delta x approaching 0, okay, then it's actually approaching the dx. Okay, so as delta x approaches 0, meaning approaching a really, really small number, then essentially the delta x is becoming a very, very small change in, infinitely small change in x. We call that differential x, okay, dx. Now, so this is, imagine this to be really, really zoomed in picture, okay? But there's still a difference, right, between the delta x and the dx, as long as it's not infinitely small, okay? Now, do you see that this right here is the delta y because it's on the actual function? So if these two are considered to be the same, right? And do you see that? Here, let me change color. So do you see that from here to the actual line, right? So this length here to the actual line, that will be considered dy, right? So remember the slope of this tangent is dy over dx, okay? Dy over dx. So if I have, so I just move the line here. If I have this to be the dx, of course this has to be dy because it's constant slope throughout. True? Okay. So we can say this. We can say that the delta y over delta x is approaching, okay, dy over dx as the delta x is approaching 0. Okay, so that means dy over dx we can say is this, assuming that delta x is very, very close to 0. Okay, Jim, what we're trying to do now here is this. I want to find this delta y given the delta x without using the function. Okay, so function is always, it's potential to be very, very complicated, right? Because it could be a very, very like function that's made with lots of different like logs and sines and polynomials. Okay, a line is never that complicated. True? Yeah? So look, if I can find dy over dx at x equals a, the change in dy must be very, very close to, and in fact equivalent to, right, dy over dx, so this part here, times by delta x. Okay, so if I want to know the change, this little change here on the function, when you're given a certain amount of change in the x, you can approximate this change using the derivative function dy over dx. Okay, so this right here is called the differential. Okay, so I mean this must be simplifying something, that's why we're doing it this way. Let's say here, okay, look, this is the function, right? If I want to know, so let's say this is a and a plus delta x. So like I want to find the delta y, okay? And this is how we have to find it. Delta y is going to be f at a plus delta x minus a f at a, right? Now let's assume our function is really complicated, something like this, you know, sine of ln of, you know, cosine of x over times by another x, you know, something really complicated. Okay, it's really complicated. Doing this, right, is not a simple process, right? Especially if you don't have a calculator. Okay, even with a calculator, there might be some errors. Okay, depending on how good your calculator is. So instead of doing this, instead of plugging all our value in here, okay, what we're saying is let's just find the derivative and find one value at a. Okay, we get a nice numerical value, and use that and use a change in the x to approximate delta y. That's what we're saying here. Okay, let me show you a numerical example.